Go.
All right. So to everyone who's here for the first time and who's coming back, thanks for joining us in the Ithaca Fest. This is the third edition, I believe. So we are welcoming our first speaker, which is Francesca Guffanti from Università degli Studi di Milano. She's going to be talking about a doctrinal view of logic. With this year, we're trying to have it a discussion a bit interactive. So maybe Francesca, tell us whether you prefer questions as we go or you would like them at the end. And thanks everyone, and Francesca, take it away.
Okay, thanks Greta for the introduction, and thanks to the organizer for giving me this opportunity to talk about my work. Essentially, what I will tell you today is a little bit of what I did in my PhD thesis, which I recently submitted. Okay, so what I did in this part of my thesis is to generalize Hankin's theorem in the context of doctrines. So for those of you who are not familiar with the doctrines, I will review a few definitions and examples that I will need throughout the talk. So let's start by saying what a doctrine is. A doctrine is just a functor between the opposite category of a category with finite products and the category of posets, and so partially ordered sets and monotone function. So it's just it. A few examples. I don't know why. Okay, a few examples. Okay, the easiest example is probably the functor that sends each set to the posets of its subsets. So as base category, we take the category of sets, and then of course to each set I assign. So to a set A, I assign it the poset of its subset, and to each, what? Sorry. Cool. To each function, we can the functor assign each function to the inverse image, and this defines a doctrine. This example can be easily generalized for taking as base category any category with finite limits, and using instead of subsets, we take sub-object of objects of the base category. And this time, each arrow is sent not to the generalization of inverse image, which is the pullback function. And this is again a doctrine. Let's get to the motivating example for doctrines, which is the doctrine of formulae. So we are in the context of first-order theory. So we take a first-order theory in a first-order language. We can take it one-sorted, but also multi-sorted language. Do the work, and let's start with defining the base category. The base category is the one of context. Its objects are finite lists of distinct variables. So we take the tuple X and the tuple Y, for example, as objects. And what is a term between the tuple X and the tuple Y? It is a tuple of terms. The length of the tuple is the same of the codomain, and each term has to depend on the variables of the domain, okay? So this is the base category. We need a functor between the opposite category of context to the posets. So first of all, for each tuple of variables, we can take the set of well-formed formulae written with at most those variables. So for a given y, we take the formula of the kind alpha of y, and we can define a pre-order on this set where we say that alpha is less than or equal to beta if alpha proves beta with the theory T. This is just a pre-order, but we can take, of course, the poset reflection and define a poset. So this is the definition of the functor on object. How do we define the functor on arrows? If we take a tuple of terms, as before, we send a formula alpha of y to the formula alpha of T of X, where we substitute instead of y1, we write T1 of X, etc., and so on until ym substituted with Tm of X. And this is a formula that depends only on X. So this is actually the main example. And moreover, when I just get back for 1 second, in general, when I throughout the talk, when I will talk about doctrines, I will think the base category as variables and terms. And sometimes I will call elements of these posets P of A, I will call them formulae. So I think of P of A as the formula depending on the variable A. Okay, and P of F I will interpret it as a substitution and so on. So I will confuse the doctrine language with the first order language in some sense. Okay, for two given doctrines P and R, we can define doctrine homomorphism, which a doctrine homomorphism is a pair, capital F, little f, where capital F is a functor between the base categories, and of course it has to preserve finite products, which is the structure that we have on C and D. And then we need a natural transformation, which is kind of the interpretation of the first doctrine in the second one. So we need a natural transformation from P to F composed R. And sometimes I will call doctrine homomorphism models. And doctrines actually organize in a two category, but for this talk we will need just the one category structure, so I will stop here. Let's add some structure to doctrines, because doctrines per se has, the posets P of A are just posets, but for example, the doctrine of formulae have much more structure. For example, given two formulae, we can take conjunction of formulae. And so what do we need if we want to interpret conjunctions in doctrine? We need primary doctrines. So each poset P of A has finite meets, and meets are preserved by substitution, so by reindexing. Okay, so in a primary doctrine we can talk about conjunction, and the T is the top element, so it is the truth value. We can add even more structure. For example, if we want to talk about implication of formula, we need an implicational doctrines. If we want to talk about both the truth and the falsum, so we need a top element and a bottom element in each poset P of A, and we talk about bounded doctrines. And of course, and then if we endow each poset P of A with the operation, then make it a Boolean algebra, we talk about Boolean doctrines. Another kind of structure that we will need is the one of existential doctrines. Okay, so we take a primary doctrine. We need the existential doctrine if we want to generalize existential quantifier. Existential quantifier is the left adjoint of some reindexing. How does it work? We take a pair of objects, B and C. So remember, I think as P of C times B as the formula that depends only on the variables C and B. And then, of course, we can take the first projection from C times B to C and take the reindexing, so the image through P of this projection. So we, of course, have this map, this monotone map, which represents the inclusion of formula that depends only on C into formula that depends on variables C and B, just to give you an idea. And the existential quantifier is the left adjoint of this map. So in the case of well-formed formula, we take an alpha of depending on C and B and send it to exists B alpha of CB. And this is a formula that depends only on C. And then some other properties has to be satisfied, but this is just the main core of the existential quantifier. And of course, we say that doctrinal homomorphism have all these properties. So doctrinal homomorphism is primary, implicational, bounded, etc. If both doctrines, the domain and the codomain, have those properties, and if the natural transformation preserves in some sense the structure. Okay. Let's see the example seen before. The doctrine of subsets is both Boolean and existential, and the existential quantifier, so the left adjoint to the pre-image, is given by the image through the first projection. Then let me just briefly say that the doctrine of subobject is always primary. And for example, if we want it to be existential, we need for the base category to be irregular. And then, of course, our motivating example is both Boolean and existential. Okay. Now that we have our groundwork all set, let's see what I tried to do. Let's see the aim of this talk. So what I tried to do was to interpret Hankin's theorem in the language of doctrine. So Hankin's theorem, I think, is well known. It states that for a given theory, consistent theory in a first-order language, if T is a theory in a first-order language, if T is consistent, then T has a model. So I wanted to interpret this theorem in the context of doctrines. So instead of having a consistent theory in a first-order language, I wanted a doctrine with some properties that we will analyze later in this talk. And instead of a model of the theory, we want a doctrinal homomorphism. As I said before, a doctrinal homomorphism and models are linked in some way. So we want a doctrinal homomorphism from our suitable starting doctrine to the doctrine of subsets. And note that I added this little star because I want the base category without the empty set. So it is still a doctrine. And this reflects the fact that sometimes when in model theory, we ask for models to be non-empty. So this makes sense some way. Okay. Let's see what are the steps of Hankin proofs that I tried to adapt to doctrines. Of course, these are just some of the steps that he did, and these are the ones that I tried to translate in this wider language, let's say it like this. So some of Hankin's ideas were, first of all, adding from the starting language, he added to the language a suitable amount of constants. And then he saw that he thought of the starting theory T seen as a theory in the extended language and added to the theory formulae of this kind. So for any phi, he added formula exists x, phi of x implies phi of c, where this little c is one of the constant added in the first step. Then he showed that after adding all of this new axiom to the theory, the starting theory was still consistent. I didn't say what consistent is, but a theory is consistent if it does not prove the falsum. Okay, and and the last main step, main idea that he adds, was to define a model of the theory T, actually of the extended theory, by taking as underlying set the set of closed terms of the extended language. Closed terms are those terms that do not depend on any variables. So these are the ideas that I translated. How did I translate all of these ideas? So first of all, before adding a lots of constant to a language, I wanted to understand what it means to add one constant to a language, and then adding a suitable amount of constants. To do this process, which is adding a lots of constants, I needed a small base category. So here there are the assumption that I have to make on P, and I will explain them to you in this slide. So small base category was added in order to be able to add a suitable amount of constant. Then, of course, if I want to extend the theory with many axioms, first I need to understand how to add one axiom and then many axioms. So to do this, of course, I needed an existential implicational doctrine because the formulae that I added to the theory are of this kind. So exists x, phi of x implies phi of c, which means that I need the existential quantifier and the implication. So that's it. And then to show that consistency still holds, first of all, let's say that I need a bounded doctrine, meaning that I want to be able to talk about both the truth and the falsum. And then to prove that after having added all of these axioms, to show that consistency still holds, I need each fiber to be non-trivial, meaning that in each set of formulae P of A, okay, for any object A, I want the truth and the falsum to be different from each other, which is a reasonable thing to ask. And then I translated the last step by defining a suitable model, and the base functor that I defined is given by homomorphism from the terminal object to any fixed object. And this reflects the fact that Henkin used closed terms as underlying set, because closed terms are terms that do not depend on any variables, which means that they are arrows. Those are arrows starting from the empty list. Okay, and the empty list is the terminal object of the category of context, and so it is homomorphism starting from the terminal object. So these are the main steps that I want to adapt. So I want to tell you something about what it means to add a constant and an axiom, because these are quite easy to understand, and so these are, I mean, they are easy to explain, while other parts of calculation that I did are not so easy. So I want to show you this part. Okay, so let's start with any doctrine P and fix an object in the base category. I want to add a constant of type X. So of course, so the new doctrine will be called P of X, and this P of X has to have as a base category a different category from C, because recall that C represents variables and terms, and if I add a constant to a language, of course, variables do not change, so objects of C of X are the same as C, but terms will change because I added a constant. So what is an arrow in C of X between an object A and object B? It is nothing but an arrow of the base category C from X times A to B. So this is the definition of the base category, and observe that we actually added a constant. Indeed, there exists an arrow from the terminal object to X in this new category C of X, and that new arrow is the identity. Okay, because if we want something from the terminal object to X, we need something from X times terminal object, which is X to X. Okay. What about the formula? So the definition of the doctrine on object and arrows of this category. What is a formula that depends on variable B, but with an added constant of type X? This will just be the old formula that depends on X and B. But if we look at the formula here, alpha of X B, it's just this is if we think of X as a constant, this is a formula that depends only on B in the extended language, and this can be extended also to interpretation of terms, and this defines a functor and a doctrine, and also a doctrine. Okay. Another thing to observe is that doing these constructions defines a doctrine homomorphism from P to P of X. The functor between the base category is the identity on object and sends an arrow F to the projection. We need, okay, an arrow from A to B is actually an arrow from X times A to B. So we take the projection and then B, and then F for going to B. And then we define the natural transformation like this, meaning that we take an alpha that depends on the variable A, and we look at this formula in the extended language. So the formula stays itself, but because it did not depend on the constant at the beginning. Okay. So the nice thing of this construction is that all the properties that P might have are preserved, meaning that if P is primary, implicational, Boolean, and all the properties the structure we added before, then both the new doctrine P of X and the homomorphism we defined also have all these properties. Moreover, this construction has a nice universal property. Maybe I will tell you something about this later if I have time. Okay. Similarly, we can study what it means to add an axiom to a theory. What's an axiom? An axiom has to be a formula that do not depend on any variable. So phi has to, a new axiom phi has to belong to P of T, the fiber over the terminal object. So it does not depend on any variable. And of course, the base category of this new doctrine is the same, because we are adding an axiom, so we're not changing the language. So C stays the same, and we just define the new sets of formulae, which are the previous the formulae of the starting doctrine, but that are less than or equal of phi, but seen in P of P. Okay. As before, we can define a homomorphism between P and P of phi. And the nice thing to observe is that this homomorphism sends the formula phi, which is the new axiom, to the top element. So sends phi to the truth, because phi is sent to phi conjunction, meet inf with phi, and phi is the top element of P phi of T. Okay, the process of adding a constant can be done for any doctrine, while adding axiom, for adding axiom, I need a primary doctrine. So, of course, P of phi and the homomorphism preserve the structure, the conjunction of the conjunction. And if we add more properties to P, all the properties are preserved. And also this construction has a nice universal property. Let's go into the more technical part. Okay, so we start, so we move forward improving Hankin's theorem. So we start from an implicational existential doctrine with a small base category. Here, I do not want to give you details of this construction, but just know that starting from P, I did a colimit in the category of doctrines and obtain the new doctrine P underline P, in which we have a lot of new constant added. And then starting from from underline P, I built a new doctrine P arrow, in which for each phi, a formula of this kind are all made true. And all of these constants are taken as in Hankin's proof. All these constants are the one added in the first step. What I did with this process was to build a rich doctrine. What's a rich doctrine? We define an existential doctrine to be rich if for any object and any formula in the fiber of that object, there exists an arrow from T to A, which means closed terms, that witnesses, let's say, the existential quantifier. So if we think this as first in first order language, this inequality means that exists A sigma of A proves sigma of D, sigma evaluated in the term D. Let's see a non-example and an example. The subset doctrine is not rich because, of course, there is, in particular, if a doctrine is rich for any object, there exists an arrow from the terminal object to that object, but there is no arrow from the singleton to the empty object, to the empty set. So this doctrine is not rich. However, if we remove the empty set, the doctrine P star becomes rich. So if we call F the composition of these two homomorphisms, this homomorphism preserves all the structures. and the doctrine P arrow is rich. So it has this property. Why is this true? Just to give you an idea, I made through all of formula of this kind, so this inequality holds. And this homomorphism has a weak universal property. This is different than what we've seen before, because adding constant and axiom had a strong universal property, and in this case it is just a weak universal property, but it is still nice. Okay, let's see what we can say about consistency. So if we take a bounded, we say that a bounded doctrine is consistent if the top element and the bottom element are different in the fiber of the terminal object. But it is so in order to have the arriving doctrine of this construction, so P arrow, in order to have it to be consistent, it is not enough to ask for the starting doctrine to be consistent, but we wanted to have each fiber non-trivial. So and in any P of A, the top and the bottom element has to be different. If this happens in a bounded existential and implicational doctrine, the arriving doctrine P arrow is consistent. And this proposition is easy to prove in the Boolean case, just a straightforward generalization of Hankin's proof. And then using some other tools, we can prove it also in the implicational case and not just in the Boolean case, using the weak universal property that I told you about before. Okay, just a quick reminder of about filters. Okay, this lemma is well known for Boolean algebras. For a given proper filter in a Boolean algebra, there exists a maximal filter extending the proper filter. But this lemma can be, it still holds in a bounded implicative semilattice. And this is something I will need in a moment. So why did we try to build a rich doctrine? It is because for a rich doctrine, it is quite easy in some sense to build a model, which is, as said before, a homomorphism in the doctrine P star. Okay, so to do this, just know that for any given filter in the fiber over the terminal object, it is possible to define a quotient doctrine in which every fiber is some proper quotient of the starting fibers. So P of X, P nabla of X is a quotient of P of X for each object X in C. And in order to define a model of this doctrine, we need a functor between the base categories and a natural transformation. So the functor between the base category is, as seen before, the homomorphism from the terminal object. So this is the translation of Hankin's idea. And then we can define also a nice natural transformation, making this pair a doctrine homomorphism. All the structure is preserved. And why did I need a rich doctrine? I need a rich doctrine in order to have the existential quantifier to be preserved. And also, sorry, I didn't say it, but I needed a maximal filter. And I needed this because I wanted to the implication to be preserved. Of course, the maximum filter exists because the starting doctrine is consistent. Okay, so now we are ready to put all of this together, and we can generalize Hankin's theorem. So let's start with a bounded existential implicational doctrine with non-trivial fibers and a small base category. This allows us to build, as seen in the previous slides, a morphism between P and P arrow. This preserves all the structure that we have had before, and the arriving doctrine is both consistent and rich. But since it is consistent and rich, we can, let me just get back here, we can apply this construction because we have because here we take PRO as a starting doctrine, and it is bounded, consistent, existential, implicational, and rich. So we apply the construction in the previous slide to build a model, gamma G, of this quotient, because there exists a maximal filter in making all of a maximum filter in PRO of T. So we just take the composition of all of these homomorphisms, and they all preserve the structure. And this composition defines a model of P in P star. And I think that I can conclude here, and thank you for the attention.
Thank you, Francesca, for the very cool talk and for being on time. So we have a couple of minutes for questions. So if you have any, please raise your hand or open the camera and just move around so that we can see you. Okay, so I see that Ivan has a question, so please.
Hello. So I actually have a number of questions.
Okay.
So the most important one is, so there is a very old proof by Joyal of completeness of first order logic, where this proof is not very well accounted in the literature, but it appears somehow in Sketches of an Elephant. So I can give some reference for that. Mm-hmm. And what he's doing there is kind of doing Enkin proof, but for coherent categories, where you have a kind of tautological doctrine structure over it.
Okay.
So I wanted to know whether you were aware of this, and what's the connection with your work?
No, I wasn't aware of this. So if you can send me this, if you can send me it, I will be happy to look at it.
Okay. And then concerning slide 22.
Okay. Yeah.
So here, the model you built, mm-hmm. Is it also conservative, meaning that, like, can I use it to test whether something is true in my doctrine or not? Because this is what Enkin proof at the end of the day does for us in first order logic.
Okay, I mean, Henkin's theorem is, okay, in first order logic, of course, we can use Henkin's theorem to prove completeness theorem.
Exactly.
I don't think so, because I think that if the starting doctrine is Boolean, we can do something more, but with just implicational structure,
But that's the meaning of the question. I don't care about a yes/no answer. I care about, like, how much false and how much true is the answer to my question.
I don't know.
Okay, so maybe we can move on to a couple of more questions. Mm-hmm. So Emilia had a question, and there's a raised hand from Genova. So I can't see Emilia anymore, so maybe Genova can speak up.
Okay, thanks for the talk. So I was wondering, do you also know, have you thought about how to add function symbols instead of just constants?
I tried it for some time, but it was really hard. I mean, I couldn't make any sense of to the base category, because
right. I mean, I guess that if the base category is Cartesian closed, then we can add a constant of the exponential, and that will work as a function symbol maybe.
But in general,
yeah, that doesn't happen for syntactic doctrines. So, I mean, they're not Cartesian closed usually.
Mm-hmm. So yeah, I've tried it, but I did not have much success in doing that. So.
Okay, so the Kleisli of that comonad doesn't work, or doesn't work like in that same way.
Maybe it works, but I couldn't do it.
Okay, thanks.
Thanks for the question.
And there is one last question, but it's from the next speaker, so he of course can do it. Please, Matthias.
Francesca, thanks for the talk. I remember you had a result about consistent doctrines and doctrines with non-trivial fibers.
Yeah.
This is a very simple question. If I remember correctly, you had that one. So if each fiber is non-trivial, then the one doctrine is consistent.
Yeah.
So the question is the following. Assume that in your base category, which must have a terminal object, every object has a point.
Yeah, then
This is-
the converse also holds. Yeah, but since in general we do not have arrows into any object, we need to ask for each fiber to be non-trivial.
Can you think of what's the easiest example of a useful base category without enough points? So I'm so used to that kind of site that now it's, I mean, a poset could be an example, but I don't know if they're useful.
No, sorry, I didn't hear you. Can you repeat? Sorry.
It was just a comment. Never mind about my comment. Do you have an example of useful base category that doesn't have enough points?
Okay. Well, set the subset doctrine. I mean, set
Right.
doesn't have an arrow from the terminal object to the empty set. Which is why I wanted to remove the empty set at some point.
Yeah. Okay. Thanks.
But
All
also, if I have the category, if I consider the category of context, and if I don't have any constant, I think that I cannot write any term, not depending on any variable.
Yeah.
So this could be a couple of examples.
Okay. Thanks.
You're welcome.
All right. And let's thank Francesca again and you all for the very nice discussion. We can continue.
There's another.
Yes. So maybe Millie, if you can stick around, we can continue the discussion later after the last talk. Because
Actually, I wanted to apologize in advance for the next speakers, but I have teaching duties and I have to leave in like 10 minutes. So.
Okay, so we can have it be very, very quick. Please, Millie.
Maybe you have already answered, but the construction of adding one constant and the construction of adding one action are special instances of more general constructions. The comma categories is adding to a category constant in general, and the adding the action corresponds to work in the comprehension category. I don't know if it can be done a relation on this reconstruction of a doctrine. And this is my question. Okay. Just a comment to relate this. You do an instances of these constructions and you lift the doctrine on instead of the whole slice category on X, only on those objects that come from the C, which are called simple type. Okay. So okay, anyway, this is a comment that those are instances of more general construction.
Okay.
Okay, thank you very much. Bye-bye.
Thank you.
So I will leave in the middle of the next talk. So bye everyone, and it has been nice doing this talk. Thank you. Thanks again.
Thank you, Francesca. Now, if you can please, yes, stop sharing. We have next speaker coming up. So Matthias, can you